Hello everyone, welcome back. In this video we're going to talk about atomic packing factor. Atomic packing factor, for all the crystal structure that we covered them, as I told you, I'll come back to it. It's an indication to tell us that how much packed the crystal structure. Imagine you have a box and you have a lot of small balls. You're going to try to put all of them inside the box. Now because they are round, you will try to arrange them. Yes, you'll put them inside the box until it will be full, and then you'll try to press them. If there is a void, you'll put the balls inside it. You will not be able to fill without any void. Why? Because they are round. When they're touching each other, there will be a gap, a void between them. So when we have those crystal structures from simple cubic, BCC, FCC, HCP, all of them, because the atoms are round, there will be gap, there will be void between them. So how packed they are, we can find this one with a calculation we call atomic packing factor. Atomic packing factor. So let's say this is written atomic packing factor. Atomic packing factor, it will be a ratio less than 1. So atomic packing factor always will be less than 1. I mean APF always will be less than 1, because 1 means no void. If atomic packing factor is 1, means no void, and it's not gonna happen. Why? Because the atoms are round. When you combine them together, there will still be a gap between them, so you will not end up 1. In fact, we cannot even go close to 1. So we're going to tell you the highest atomic packing factor we have. Now, if you remember, we said that simple cubic has a low packing density. Why? Because there's a lot of void there. A lot of voids we have it. When the atoms are touching in this, arrange themselves in this manner, there will be a big void in between them. So how do we calculate this atomic packing factor? Atomic packing factor, it's easy. We just want to know that in this cube, the volume of the atom within this cube, that's what does it mean. The volume, I mean, look, this is a volume of this atom here, yes? I mean, we have how many of this one? 8 of this one. So if I calculate the volume of this portion times 8, that will be the volume of solid. Imagine the volume of solid within this cube. So we have two parts. Let me just make it somehow understandable for you. There will be volume of cube, volume of the cube. Now the volume of the cube is just A. It's A cube, yes? It's A cube. Now we want to find something else, volume of atoms. Volume of atoms. We need to know, for example, the volume of those atoms. Then we know that what will be the amount of solid within this volume. Imagine this one as what? You have a cup of water, Now, you know the volume of this cup, and there is water inside it. Yes? Now make this one easy for understanding. There is a cup of water, you have it, and let's say the volume of the cup, it's 100, whatever it is, cc or milliliter, whatever you call it. Let's say the volume of the water inside it, is 50. Let's say 50 milligram. Now what do you say? Now, is this cup full? No. Is this half full? Yes. 50 over 100. Look, if I say 50 over 100, it's gonna be 0.5, yes? 0.5. I mean, if I multiply this one by 100 as well, multiplied by 100 to make it percentage, I can say that 50%, look, 50% is full. We know that it's 50%, yes? 50%, because it's half of the cup is full. An atomic packing factor is similar. We want to know the volume of the atoms, and we imagine the atoms are the water, because it's filling this cup, and the cup will be the cube. This is the volume of the cup, and this is the volume of the water. So we want to know that, and then we divide the volume of the atom by the volume of the cube multiplied by 100, or no need to multiply it by 100, it still be okay. Yes, if someone can say that 0.5 is enough. Yes, 0.5 is enough. 0.5 means half full. This is what we're going to do. So we're going to calculate for each of those crystal structure, volume of cube and volume of atom. Now I'm gonna start with the volume of cube first. Remember, in simple cubic we say A is equal to 2r. Yes, 2r. So it's gonna be A cube, gonna be 8r cube. If you say A cube here, it's gonna be like this. Yes, it's gonna be 8. 2 times 2 times 2 is gonna be 8. 8r cube we have. Now this is, look, this is the volume of this cube, with regarding to r. Now we're going to calculate volume of atoms. How many atoms do we have inside a simple cubic crystal structure? We calculated number of atom. We had 8 corner, each corner 1 over 8. We have 1 atom. So we have 1 atom multiplied by volume of atom. Since the atom is sphere, we know volume of sphere is equal to what? This volume of sphere, 4 over 3 pi r cube. This is volume of sphere. 4 over 3 pi times r cube. We have 1 atom. We calculate number of atom, and the volume of atom is sphere, 4 over 3 pi. 4 over 3 pi r cube. Now we will say that, let's calculate the atomic packing factor. It's equal to the volume of atoms, so volume of atoms here, over volume of the cell, the unit cell we have it, the cube we calculated. So that's gonna be, we had 8 r cube, and at the top we had 4 over 3 pi r cube. So r cube is gonna cancel r cube. So if you divide this one by each other, let me just check, we will have, I'm not gonna multiply it by 100 here, but you can multiply by 100 as well. I mean, atomic packing factor, as a factor they wrote it here, There's something they call atomic packing ratio. They will make it 100%, but this factor here in our book, atomic packing factor, we can just leave it as a factor to see how much it is. So 4 divided by 3 times pi divided by 8, we're gonna have 0.52. I'm gonna put 0.5236. So it means any crystal structure which is simple cubic, this will be the atomic packing factor. I mean, this, what does it mean? I mean, if I make it percentage, it will be 52% it's solid, 52% is atom, the rest is void. Look, a big void we have it here. 52% it's solid, so within this cube 52% is solid, the rest of it is void. This is, we calculated here. Now this is the base of atomic packing factor. Let's calculate it for FCC. for FCC atomic packing. We're going to calculate it for FCC. Now, we know atomic packing factor. Atomic packing factor is equal to volume of atoms over volume of cell. Look, this is S here because we may have different atoms inside each crystal structure, but all of them will be the same equation over cell, or unit cell we call it. We have it here. Now, the volume of cell here, well, the cube is equal to what? It's still a cube, yes? But what's the problem? What's the difference we have it between this and the other one? Here, A. You remember we calculate A to be equal to 2 root 2 R. Yes? 2 root 2 R. So when you cube it here, we have it root 2. So I'm going to write it in this manner, all of them, because the number will be long. I don't want to write it down. Or you're going to cube this one here. So let's make it in this way. Let's say this is cube and the 3 is cube. The 3 is cube. So this number cube and R cube, that's going to be the volume of this cube. Why? Because A depends on R, and we know that A is equal to 2 root 2 R. So this is going to be the volume. This is going to be the volume of the cube. Now, we calculate the volume of atoms. We calculate how many atoms we had in FCC. We said we have 4 atoms. I mean, all of those going to give us 4 atoms inside here. So if I want to calculate volume of atoms, it's equal to 4 atoms we have it, 4 times, and volume each atom is the same, 4 over 3 pi R cube. Now when we bring them back here, it will be 16 something, so we're gonna bring them back here. This will be 16 over 3 pi R cube, and at the bottom we have 2 root 2, and this is cube, and R cube. Now R again, R cube with R cube will go. So R cube with R cube will go. If we calculate this one, we're going to get the atomic packing factor, which is the highest possibility of atomic packing factor. Now, if someone asks you to arrange, for example, 10 small balls in a box, you will use this arrangement, FCC arrangement, to fit maximum number of balls within the box that you have it. Remember this. Why? Because this is the highest arrangement that you could possibly have, or you can say minimum void that you can get, maximum density you can get when you're arranging those atoms. So it's supposed to be 0.74. I'm just double checking to see if I haven't done any mistake. 2 times root 2, 0.74, 0.74. So it means that 74% of this cube is solid and 26% is void. You cannot get higher than this. This is the highest atomic packing factor that we can get. The highest atomic packing factor we can get is 0.74. There is no way other than this that atoms can go inside each other, unless we have alloy. Alloy is different. Why? Because alloy, we will have some atoms coming in between here. We'll talk about them in chapter 4. That's going to be different. Yes, there will be some other atoms coming in between here, so we have to calculate those as well. So together we can get the full. But as one material, one element, I'm not talking about alloy here, not talking about alloy. One element, the same size of atoms, cannot be packed more than this percentage. This is 0.74. We can repeat the same thing for BCC. I believe it's here, yes, it's here. Sum of atomic volume over the volume of the unit cell. So volume 4 hard sphere, and each of them will be this. And for the unit cell, we have this one. This is the A cubic, and then divide each other, you'll get 0.74. The one I did. Maximum possible packing of hard sphere. We'll come back to this closed packing. Now we can do atomic packing factor for BCC. Let me do it as well here for BCC. Now for BCC, what do we have? Atomic packing factor. We have volume of cube. It's A cube. Now A cube here, A, the relation between A and R, we said A is equal to, it's here, it's here, A is equal to 4R over root 3. This is A. So if I go for A cube, we're just simply cubing this 4 over root 3, this side cube, and R cube. This is the volume. This is the volume. Why? Because the volume of cube is A cube. We have the volume. And how many atoms we had today? We had 2 atoms. 2 atoms and 2 timers the volume of atoms. Volume of atom. We know that they are sphere. So 2 timers 4 over 3 pi r cube. Then you know that this r cube, this one divided by this one is going to give us this 0.68 as atomic packing factor. So it's lower than the FCC. FCC is the highest, so far the highest atomic packing factor. Atomic packing factor. Now for hexagonal close packing, I'm not going to do it. I will just, last semester I gave it as a homework to students to calculate the atomic packing factor. I may just give it to you to do the atomic packing factor for me as well. So there will be, I'll give this one maybe as a homework. You'll do it for me. It will end up exactly the same thing. It will end up exactly the same as 0.74. So there is a question here. If the atomic packing factor of FCC and HCP is equal, and both of them is equal, the atomic packing factor for both of them is equal to 0.74. What does it mean? It means that the atoms will be, there is no minimum void. The arrangement are similar. The arrangement is supposed to be similar. But why we were gonna give, how we gonna get hexagonal and how we gonna get FCC? If you put those, for example, the spheres inside the box, if you put each of them in the way that they will fill the gaps between them, so how we gonna get hexagonal but not FCC? Or how we gonna get FCC not hexagonal? Why? Because both of them, they have the same atomic packing factor. What does it mean? It means that when you arrange them, let's come back here. When you arrange them, look at the arrangement, we have it here. Now the way that HCP will be different than FCC, they call the stacking. The way that they will be stacking atoms, you'll stack them together. This is going to give us a different arrangement. Still you're gonna get the same atomic packing factor, but in HCP, so let's talk about this way to see how the sequence is placing. Let's see from here. I don't know if you can have understanding. For example, this is the layer, put them, yes, this is the layer at the bottom. If you're trying to imagine, this is the bottom of the box. Imagine this is the bottom of the box. Someone is trying to tell you that, okay, place the balls inside the box. You place those spheres in the bottom. Then what were you going to do? You're going to place a different, you have more, yes, you have more, and you're trying to place them here. This is what you do. You're trying to put them in the spacing. So you're going to try to put in this void. This will be the second layer. You're going to put inside this, inside the I mean the gap that you have, and you try to put the ball, the spheres inside here. Those gap will be the second layer, yes, the second layer. Now for the third layer, what will you do? You're trying to put, I mean still you couldn't cover this one, yes, you're gonna put something here. There will be three, look, there will be three, there will be one here, there will be one here when we put them, and those three, there will be one here, those three will create another void, then you're trying to put the third layer will come here, the third layer will come here. Now imagine if I go for the blue one, let me just do the blue one. Let's say this is one, we put it here. It'll be big, something like this. There'll be one here. I'm trying to at least do some. This is the second layer, I mean the second layer we're trying to put. It'll be round, but I cannot create this much big atoms. Now they will be touching each other, all of these. So what will happen for the third layer? For the third layer, we'll be having gap between them. Then we're gonna go fill. We're gonna put the third one in the gap between them. And we're gonna put in the gap between them, and that's gonna give us the third layer. So if I check this one, I'm gonna show this one to you in a 3D to see how does it look like. How does this look like in a 3D? It's gonna be something like this. Look, we had one there, we place one in the void, then we place the third layer on the second layer's void. That's gonna give us FCC crystal structure. This is how the scattering, they call the sequence, they call it ABC. A is layer 1, so this is layer 1A. There is another layer, layer B. There is another layer C. That's gonna give us FCC crystal structure. They call the stacking sequence. ABC, ABC, repeating this one. ABC, ABC. That's gonna give us FCC. Well, for the HCP, what will you do? You will place the atoms here. You'll place the atoms here. I mean, this will be the atom we have it, yes. So we can put some atoms the way that they are. They're supposed to touch each other. Let's make it a bit bigger. So we have this. So we can at least, we'll put over the gaps. So one will come here. One will be somewhere here. That will be somewhere here. And in continuing this manner, you will have a sequence. We have it here. I can do this one for the top as well. So you realize that I put those atoms basically on the void that coming between on the layer A. Now, in order to continue, what we will do, we're not gonna put over here, we're gonna put again over the same layer. We're gonna put over the same layer. So the second time we're gonna put those, we're gonna again put it back in this place here. So what we do, we're trying to put another atom again back on this layer here. We're gonna use the same location of the first layer. That's why we call them A, B. We're repeating A, B, and that stacking will give us hexagonal close packing crystal structure. This is we call AB. It's repeating. There is no C. The layer A will put them back. Still, you're gonna get the highest density, but because the arrangement is different, then the crystal structure will be different. This is, you look them in the 3D will be something like this. This is the way they're repeating, and there's a 3-layer repeating. That's going to give us FCC. This will be HCP. We're going to talk about this one later. I'm not going to explain this plane here, the density of this plane. What does this mean? I'll come back to this one. Even there are something inside here, but we'll come back to them. Even here, there's the density of this one. Closed pack plane, the highest density. We'll talk about this. We'll talk about this one when we explain the plane. So this is we call atomic packing factor. The highest arrangement of atoms that you can have it's from FCC and hexagonal closed pack. If you by any chance have some those spheres, you can stack them over each other. If you have a glass, we don't have that much opportunity to show it to you, but if you have a glass, put them over each other, you can create an FCC crystal structure, or you can create a hexagonal closed pack crystal structure, and you will use the same exact amount of spheres to create both of them. Why? Because closed atomic packing factor in both crystal structure are exactly the same. This is we call atomic packing factor. Now atomic packing factor for hexagonal is what? You know the number of atoms. We have 6 atoms, so you can calculate the volume of atom. The only one remaining is the volume of this hexagonal. And since I'm going to give you volume of hexagonal as an equation, so you can also use that one to calculate the atomic packing factor. I'm not sure for the homework because it's something very simple. I gave it last year, but I realized that it was not beneficial for students. Why? Because they have the equation, it's just simple calculation there. That will be enough for this week. I'm not gonna continue more. Next week we're gonna calculate density computation. Now in density computation we will use all of this crystal structure that we cover them, and we're going to discuss how we theoretically will find density by using those. We have the density calculation, so we're going to show it to you where does this came from and how we're going to calculate theoretical density of any crystal structure that we have it. Thanks for watching.